We will introduce our next speaker, which is Jonas. Take it away.
Thank you. So this is my first SecurityFest, and it's really nice to be here. Awesome conference, awesome sponsors, and yeah, really happy so far. Also nice parties. I have kind of a jazz voice today, so I probably had fun. Right. Do have some slides. Nice. So my topic is Tales from the Temp. But first, a few words about me. My name is Jonas Vestberg. I'm a senior security consultant at Sentor, and I've been there for the last 10 years. I'm a penetration tester. I do everything from web apps to Windows to AS400. So if you like AS400, please talk to me after. Nowadays, I try to focus mostly on Windows and Active Directory and do some red teaming and try to pretend to be a developer, but mostly of offensive stuff. All right. A few words about Sentor. We're based in Sweden. I think most of you know who we are. We've been here for ages, survived the dot-com boom. We got acquired by Accenture a few years ago. We do, as most do, manage security services, InfoSec, and pen testing. And this handsome guy is in the audience. Oh, this happened again. Okay, cool. All right. So this talk is about the Windows temp directory, the scary place. I'm actually going to talk about a few vulnerabilities that I found, but I'm going to start off with a lame background. I feel obligated. I'm going to talk about how I found the vulnerabilities and how they can be exploited. And they're all privilege escalation vulnerabilities on Windows in third-party products. So just to get the right context, there are few different execution modes on typical operating systems. You have user mode, you have kernel mode. If you're in a kernel, you basically control everything. But nowadays on Windows, you can't be there unless you're a sign driver, like cross-sign with Microsoft itself and everything. If you're in the user mode, you're either an application started by a standard user or a service. Services can run in different privileges. You can be an unprivileged service and a privileged service. The different kind of user privileges there are you can be standard user, you can be service, you can be an admin, or you can be a local system, which is the equivalent of root in Linux. Service is a little bit special. There are a few services that have documented escalation paths to system. So in general, if you can run code as a service, you can escalate to local system. And as an attacker, you're interested in these privileges because that will allow you to fully compromise the machine. And looking a bit about the attack surface, and now I'm talking about the attack surface from a local perspective. A local attacker is already on the system. You have like network sockets and all the different generic Windows objects that exist, like the file system, registry, RPC endpoints, name pipes, mail slots, everything. Most of these are controlled by access control lists. So you can set permissions on mostly everything, with the exception of network sockets, which is interesting, because then you only need to connect to a port. The assets that attackers are interested in is the integrity of the system itself, other systems running on other users logged in on the system. There might be a domain admin or a server admin logged in there. If you're able to compromise the machine, and then you can pivot in and use their privileges. The computer identity is interesting if you're in a domain-joined environment. And there are also local secrets, like the local password hashes, service passwords, if you run a service as a domain user, for example, and also private keys for any certificates on there. So this is what the attacker would use a privilege escalation bug to obtain. If there are no interesting assets, then you can just use the privilege that you have as a foothold to attack other things on the network. Super basic privilege escalation is the act of exploiting a bug to gain elevated access, sometimes called elevation of privilege. I think that's Microsoft's term if you look at security bulletins. There's a few different temp folders that used from different perspectives. Standard user have their temp folder under the app data. Services actually have a service profile located in the Windows directory. That's also on the app data. But if you run as local system, you have the ctemp. And that's kind of the temp directory that I'll be talking about for the rest of this presentation. Temp folders are interesting because normal folders, users can, if they have access, they can list files, they may be able to create files and subfolders. And if you are the owner of the object, like everywhere in the Windows and Active Directory, if you are the owner, you can, even if you don't have direct access, you can give yourself access. The temp directory is locked down. So standard users can't list files, but they can still create files, and they can create subfolders. And as owners, they have full permissions of the object that they create. So this is kind of how it looks. In this little screenshot, I'm a standard user trying to list ctemp, the Windows temp directory. This is the access control list. You can clearly see that the creator owner have full permissions that are inherited to subfolders. The users, the local users group, have write access that is also inherited. And then administrators and system have full permissions. So if you look to the right, you can see me as a standard user creating a test folder within the temp directory. I am the owner with full permissions, but users still have write access to create files and subfolders within that directory that I own. All right, so this is the tools that I've used. There's a few screenshots. I just want to mention them. Sysinternals have great tools for doing analysis of what processes do, what programs do on your system. Access check is if you want to look at an ACL for a name pipe that I do in this case. It's useful. And I usually just use Visual Studio for creating apps and payloads and stuff. Right. So the first product I'm going to talk about is the Snow Inventory Agent for Windows. How many people have encountered this product before? There's a few hands. It's kind of what I expected. This is an inventory software that's made for enterprises. It scans local Windows systems to see what products are used and installed, and then sends that up to a server. It's developed in Sweden. It's like their office is like 400 meters away from where I live. It's quite common when we do pen tests, and the clients that we work with long term, they quite a lot are using this product. It used to have a third-party component that was used to kind of get the capabilities of the CPU. So this is what happens when an inventory scan is performed. It's triggered by a schedule. The service then continues to extract the DLL and then load that DLL. That DLL itself extracts the driver, loads the driver. The product does the thing and then unloads the driver, removes the driver, and same thing with the DLL. So this is how it looks in the process monitor when you do this the right way. After dropping that DLL, you can see that it checks for the driver. If it doesn't exist, it creates a folder, copies the driver, loads the driver, removes the driver, and removes the folder. So this is kind of a vulnerable behavior because you drop the driver on a static location. And it's a location where normal users can create files. So the attack is pretty neat. It's what you call bring your own vulnerable driver. You just drop a vulnerable driver instead of the intended driver. You have the service loaded for you, and then you just use a public exploit to escalate privileges. This is how it looks. I'm an unprivileged user. I have a very advanced apt batch script, which does all the magic. It just creates it copies the vulnerable driver. It then continues to remove privileges for the system identity, because we don't want it to overwrite a driver or remove it. And that kind of works. Then wait for the inventory to be triggered, which I'm doing in the background, just restarting the server. And then, on system. Thank you. So this is kind of what happened in more detail. Me as an unprivileged user, create a folder, copies the vulnerable driver, restrict permissions for system, wait for a scheduled inventory, and then use a copy-pasted exploit from Metasploit to do the hard work. Yeah, that's me coding, copy-paste on GitHub. All right, so this is how it looks in Process Monitor when the driver is already there. So the service is kind of lazy. It checks if the driver exists. Yeah, it exists, but it just continues anyway. It tries to create a folder. It's already there. Loads the driver. Then tries to remove the driver file, and fails. So it could be more picky, I think. So the timeline here is that I reported this through a friend that works there. He kind of speedrun the contact to one of the product security guys. I reported the vulnerability because this is in the third-party component CPU ID SDK. I reported it to the developer, and they presented a fix shortly after that I verified. And then 3 years later, there was a security bulletin that sounded kind of familiar, so I had a look at it. And the same exploit just worked out of the box. So I was fairly certain that this was the exact same bug, but their product security team was like, no, we found this in a private bug bounty. It's not the same bug. Okay, I'm actually not sure. It doesn't matter. Everything before version 6, 7, 8 is vulnerable. They remove this component from that version, and there's a workaround for anything before that. And I'm not super unhappy with this because we did a pen test around this time. So now that I knew that it worked on later versions, we were able to kind of abuse that to Privesc on some Citrix systems. It's always fun to use your own bug to do evil things. Right, so the next product I'm going to talk about is the F5 BigIP Edge Client for Windows. And this is a VPN client software, and as VPN client softwares do, they install like 5 services that's running as a local system on your client. Those services do things like open the tunnel, do compliance checks, and of course you need something to install stuff, like an agent. I was helping a client out on a kind of a long-term gig. They were running this product on all their clients, and I read this security bulletin from another researcher, and I wanted to verify the fix. This was a vulnerability in the component installer service, and that can be used to install MSI packages, EXEs, or CAB files. They do code signing checks, and they store stuff in the temp folder. The first thing we need to do to exploit or to kind of look at the behavior is find a way to trigger an installation. So I found this named pipe pretty early. It was fairly obvious that it was relevant. So I wrote a custom client for that, which probably took like half the research time because I was a terrible coder at that time. As you can see on the ACL, only system and administrators have access to talk to this pipe, but we also have the interactive identity. And this is given to all the applications started by an interactive session. So if you manage to exploit a service, for example, you won't be able to talk to this pipe. But if you're Notepad, then you can talk to it. All right. They do code signing. They have authentic code signatures on all their components, and they only approve to install components signed by a short list of CAs, or actually short list of certificates that they have kind of bundled. I was able to bypass the code signature in this case simply by using DLL hijacking, because since all their own binaries are signed by them, I can trigger the installations of those programs. And this is how it looks. You can see the static path. I'm using an exe called cachecleaner.exe. And this is process monitor once again. You can see that it tries to load the DLL from the same directory. And this is kind of typical for DLL hijacking vulnerabilities. So this is me again. Very advanced bat file once again. I'm creating the static path, the F5 temp. I'm copying a DLL payload, which basically just runs netcat as a bind shell. I trigger an install with my custom client of the cachecleaner exe, and then just connect. It goes fast. Okay, so this is what happens in more detail. I, as an unprivileged user, create the temp folder once again, copies the payload to the cachecleaner DLL location, send the exe over the name pipe. The service will save that file in the temp folder, execute the cachecleaner.exe, though at the same time sideloading the cachecleaner DLL, and my payload is executed as system. So now I have verified the fixed vulnerability, and now I'm going to look at the next version where it's fixed. They didn't change anything, so I can use my custom client to send files to the service. And I noticed that there were a thread ID and a timestamp within the temporary path. So they tried to add some random data to it. And exe files were no longer supported. So to bypass this, it's not a super good solution because the thread ID is like kind of a global ID that you can query using Windows APIs. And the timestamp is just a timestamp. I can query that too. And cab files are still supported. So this is kind of how the new temp directory looks. It looks scary at first, but then you kind of notice that there's no entropy in there. So to bypass this, we need to guess the temp folder. We need to bypass the code signatures for cab files, and then we need to find a way to execute code using cab files. So first, to guess the temp folder, we can use the Windows API create tool help snapshot. That's kind of the API that you use when you want to list processes and threads. There are multiple threads within the service process, so it's kind of challenging. To get the timestamp, this is the timestamp that the service uses. It's the get tick count, which is, I think it's millisecond precision from where the system was started. It's a bit of a delicate timing because you need to create, to exploit this, you need to create a bunch of folders. I'm going to get into that soon. But the positive thing is that we know when the file is created because we are the one triggering it, and we have basically unlimited attempts. So if we fail like the first 5 times, we can continue. All right. So first we list the thread IDs of the service process. Then we select one of the threads. Usually the second thread is the one that's used by the installer. We call the tick count, and then we add a small offset because we want to pre-create all the folders so that you can win this race. Then we trigger a installation through the name pipe, and then just hope for the best. So I try to visualize kind of how the attack works. My exploit tries to create all the different folders with different timestamps for a certain thread ID, and then just based on timing, the service will hit one of those folders, and we win our race. And this is how it looks in Process Monitor when I win my race. As you can see here, is a name collision, which means that, or I'm gonna bring my laser pointer. Here we see a name collision, and that means that the folder already exists, and I was the one that created it. And this is my custom client that continues to create folders, actually symlinks, but basically folders. Right? Then the next step is to bypass the code signatures. Because now we won the race, but we still need to send something there that they will trigger an installation of. So when I looked at the behavior, I could see that it began with writing the file to the temp folder, and then it, in a number of steps, verified the code signature, and then finally it began to install the cab file. So what we need to do is still guess the temp folder, and then just present a signed cab for the check, and then at the last step, just switch in an unsigned cab. To continue to explain this attack, we need to go through some basics. So there's something called oplocks, which is opportunistic locks. This means that you can create a lock for a certain file operation on a file, which blocks execution for other threads trying to read that file. And if we created that lock, we can also release the lock, which makes it possible for us to control the timing. And this can be done using a proof of concept tool from Google Project Zero. And this is how it looks in the most kind of basic situation. We have a file. I can create an oplock on that file just to show that how execution is stalled when another thread is trying to open that. And then I go back to the first console window and release the lock. So this is great when you're trying to exploit timing vulnerabilities. And there's also something called symlinks, and this is like super duper basic if you're used to Linux. But symlinks, yeah, it's a reference, it's a weak reference to a file. The file does not have to exist, it's just a loose reference. Symlinks do exist in the NTFS file system, but on Windows, you can't create symlinks unless you have admin privileges by default. But there are certain technique that can be used to create something that is the equivalent of symlinks. Using directory junctions, which is basically the same thing as a symlink, but only for directories. And then you have a link in the object manager that will then later reference a file. So you basically create a junction, pointing that to a certain category in the object manager, and then within the object manager you have a link to the file. This does not require admin privileges, but it has a few other requirements. And there's also a proof of concept from the same Google Zero project. This is how a junction looks like when you create it. It's actually kind of like a folder which references RPC control, and that's a kind of a category or a type within the object manager here. And here I created a symlink within the object manager that references a file on another location. Right, so this is an example of using that to create a symlink. I create a junction called test files and a symlink called test.txt. And I reference that to a file in a non-existing file in the system32 directory. And below is an administrator that writes to the file or to the symlink, just showing that that data will eventually end up in system32. And this is a kind of a great exploit primitive when you're looking at logic bugs on Windows. And I'm a slow typer, sorry about that. Yeah. All right. So, where were we? We wanted to kind of switcheroo in the unsigned cab at the last step. And this is, once again, process monitor showing that the service writes the file, and then it checks signature a few times, and then on the last step, it kind of parses the cab file contents and extracts it. And this is actually a timer check, timer use vulnerability, a timing vulnerability that can exploit using oplocks. You send an oplock on a file. In this case, you have like two separate read operations that are not within a transaction. So you set an oplock on a file. You wait for the victim to hit that lock. Then you release the lock, and then you switch to the bad file. And the next, when the file is actually used, you have your bad file or the bad contents in that file. But the problem is here that I have a queue of read operations, and oplocks in its basic form can't be queued. So if I have an oplock and two different threads are reading it, they both will be kind of released, or the execution for both threads will be continued when I release the lock. So I had to find a way to get around this. So I managed to kind of use symlinks to queue oplocks. So I create multiple files. I create oplocks on those files, and then I create a symlink that the kind of victim or targeted process will try to access. And then as soon as the first read operation continues, I release the lock and switch the symlink to the next file descriptor with a new lock. And then I release the lock on the second read, pass it on to the next, and on the last step, we have a clean read on the modified or the bad file. And in the example of the cab file, the actual cab was parsed on the read operation number 7. Okay, so now that we were able to bypass the code signatures, we need to still find a way to execute code using cab files. And cab files are interesting because they have a rich feature set. If you're old like me, you remember the ActiveX controls that you kind of installed through the browser in Internet Explorer ages ago. So a lot of the features were used in that scenario. You have an in file within the cab file. Cab is a file archive, first of all. And the in file kind of works as a manifest. It defines what ActiveX objects to kind of register, or what services to install, and what files are in there. So the easiest way I found, using internet archaeologist, I kind of found the documentation to set up hooks within the in file that just simply ran a command. And there are also the possibility to kind of exploit the fact that the cab file is extracted, so you can kind of switch in a DLL that you want the service to parse at a later stage. So that's another type of race condition, but it was a bit more tricky to exploit. So I'm going to use this case. I have a simple cab file with netcat, and in the in file defines a setup hook that just use netcat as a bind shell. And yeah, I craft that in file, add the netcat exe, and just make a cab from that contents. Okay, now we have everything we need to exploit this bug. So this is how it looks. It's a bit more tricky. In the bottom console window, we have the custom bait and switch. That's going to switch in the backdoored file on the read number 7. Yeah, I like my script files. I have a client that designed to win the race, so that will create like 1,000 folders that reference or represent the different timestamps in the future. So once I then trigger the installation, it wins the race and loads that cab file. Yeah, and it repeats. So thanks. Right. So they made a fix when I reported this. They had a random token within the folder, but they moved the folder to program data, which is just made it worse. Because program data is just an ordinary folder that inherits all the ACLs from Temp or the roots, I think. So this took about 20 minutes to bypass. You just monitor files within the program data folder. When that directory shows up, you just put your DLL there and wait for the service to load it. So that was disappointing. Yeah, I don't think I even needed to use an oplock, but yeah. And they produced another fix, which actually used the same random token, but they moved it back to Temp, and that's sufficient. So they got the green light. At that point, they already released the even worse version, but they didn't present any security bulletin. So this is kind of how I reported this. I found this in 2020, late in 2020. I reported it to the F5 CERT. I got a pre-release like 5 months after, which made it worse, which I reported a few days after. That still got released, but the security bulletin didn't. That's one way of doing it, I guess. And then a few weeks after they released the .3 version, I retested it and it was good. And the component installation service got a CV for the temp folder failure. I actually got a CV for the for the DLL hijacking, which is really weird because I think most their binaries can be used to do the same. But yes, okay. And even though they fixed it in the new version, an attacker would still be able to use the old versions because it's still signed. Okay, so they have a few different kind of version tracks, but it was fixed in 7212, or everything up to 7212 is vulnerable. All right, how are we on time? I think we're good. There's not a scientific results from this, but there's a few lessons learned regarding attack surface. Everything you add or everything you install on a system is an additional attack surface, especially when it's services running with high privileges. And enterprise software is typically, or enterprise products is typically something that they like the agents and the services. If you look at a typical enterprise client running on a fairly large organization, you probably see like 1 or 2 security softwares and an inventory agent and like backup software, and yeah, there's a lot of attack surface. And just because it's enterprise software doesn't mean that they actually looked at the security of the product. And I think if you look at like CV history, you'll notice that every single update service has been vulnerable to something like this at one point in time. I think that's a kind of almost a rule. Product security is hard. If you look at these 2 cases, both vendors actually failed to fix the bug that I reported. yeah, they did have good security people, and I actually don't know what the hell went wrong. I think it's something within the versioning of releases. I think they just maybe one release was actually fixed, and then the next they just used an old version of the vulnerable component. But it's kind of depressing. As a developer, you need to know your own platform. You need to know all these quirks and weird things, like the temp directory. And of course, it's important to verify fixes. Even if it's an easy fix, it's really hard, or it's really easy for developers to miss tiny details. If you're a security consultant that reports bugs and do retesting, you, of course, know this already. All right. So I totally lost control of time, but I have some extra material that we can run if we have time. Sure. My PowerPoint skills have improved. All right. So I did a presentation at Disobey earlier this year when I talked about finding vulnerabilities in offensive tooling. I looked at a number of example scripts of Impacket, and I thought one of these is kind of fits the theme, because they also fail in how they use the temp directory. So this is the SMB exec. If you don't know Impacket, it's a kind of a offensive tool set written in Python that interacts with, or they implement a number of Windows protocols from scratch. It's kind of impressive if you look back, because at the time where the project started, I don't think there were any third-party implementations of some of the RPC stuff that they implemented. But SMB exec is used for lateral movement. It's really a super duper basic script. It's used to execute code as system. It's easy because they don't deploy an agent on the target. Just create a new service, and then kind of writes a command line to the bin path of the service, and then executes that. And it happens that that command line use a static path to a script file located in the temp directory, and then it executes that and removes it. And then it writes the output to __output within the C directory. It's kind of fun if you're a blue teamer, because if you can control the contents of that file, you can kind of troll pen testers by writing fake output. Okay. So I'm not sure if this is visible, but to the left you have like an attacker or a pen tester or whatever. To the right you have me running a tool as a non-previous user. I use that to start Notepad as system. And I think you can see from the kind of comments that I create the execute script within the ctemp as a non-previous user. I'm the owner of that file. I create an op-lock on the execute BAT. When the op-lock is released, that's the time where SMB exec writes the command to that file. But since I'm the owner, I can then just replace that with my payload, and then the next step, the service will execute that file with my payload as a system. And the solution here is to, well, don't put your payload in where unprevious user, or the fix is that you should write the file somewhere that normal users can't change the contents. And it seems appropriate to use a random name as well. And this was fixed in Impacket earlier this year. This is how the vulnerable version looks like if you look at it in Process Monitor. And this is how the fixed version looks like. Every command will be executed in a separate file. Right, that's it. Thank you.
Thank you so much. Do we have any questions? Anyone? Any questions? Everyone is very shy today. I don't know why.
I think we have one there.
I think we have one over here.
One over here. Go. Go.
Hi.
Hi.
Thanks for the talk. I wanted to ask you about when you gave the information to the team to fix the temp, and then they replaced it with program data.
Yeah.
Did they have all the context to know why that's a bad thing, or?
I mean, I didn't. My recommendation were to move it to the service profile under System 32. That's a directory where standard users can't create files or even read files. They obviously didn't listen, and they put it in program data instead. So I have no idea what happened. It took like 5 months, so it wasn't like we had daily contact either.
Okay, anyone else?
No?
It's fairly common that applications use program data for temporary files, and that's okay as long as you when you deploy the application, create a folder and restrict access to system, basically. And that's typically what you see.
Thank you so much.
Right. Thanks.